Welcome to our discussion on horizontal motion and falling. Today we're going to be talking about how sideways horizontal motion affects the fall of an object. Let's get started. So the question we're trying to answer here is, how does the horizontal motion, that sideways motion, affect falling? And in the lab you slid a washer along the table, and as that washer slid and fell off the table, it bumped into another washer that was sitting right on the edge. So that washer on the edge just barely fell off the table and fell straight down, while the sliding washer fell like this, out to the front. And you were able to compare which one hit the ground first. And using your video from your phone that you took, as well as hearing it and seeing it, we came to the conclusion that these things are hitting at the same time. Even when we slide this one super fast and it goes way over here somewhere, it hits the ground at the same time the one that just dropped is. Today we're going to try to get a better understanding of why that is. To do that, we need to first look at what happens to an object when we just drop it. So we have an object here that we drop, and we need to figure out where it is at different time intervals as it falls down. Now, because it's a table and this is not very tall, we're going to be looking at it every tenth of a second instead of every second. If we were doing every second, we'd need like a 120-meter table to be able to get enough data points to make it make sense. So we're looking at tenths of a second here. And we'll be using, of course, the equation of delta H is equal to 1/2 AT squared. Now remember, A is equal to 10 meters per second. And the one we're going to be using today is not for meters, but for centimeters. And that acceleration is equal to 1,000 centimeters per second. And of course, both of those are negative. So we'll be using that in this equation along with these small times to calculate our change in height. Now remember, our change in height is from our starting point. So if you get a negative 5 centimeters, that means it's 5 centimeters below your starting point. That's the negative change mean. Alright, so when we plug these guys in, we find that delta H is equal to 1/2 times 1,000 is negative 500 meters per second, and that's going to be times t squared each time. Now when you plug in 0.1 for t squared and multiply by 500, you get an answer, that should be centimeters, sorry. You get an answer of 5 centimeters. For 0.2 seconds, when you square it and multiply by negative 500, you get an answer of negative 20 centimeters. And for 0.3, you get a negative 45 centimeter, and then a negative 80 centimeters, and then a negative 125 centimeters. Now notice these numbers keep getting bigger each time. That's because as we fall, we speed up, right? So let's go ahead and plot this. So at 0.1 seconds is at 5 centimeters, and if this is 20, here's 10, here's about 5. So at 0.1 seconds it's here. At 0.2 seconds, it's at negative 20, so it's 20 below where it was, so it's right there. And at negative 3, it's at 45, and here's 50, so here's about 45-ish. And then at negative, or 0.4, it's at negative 80, so it's here-ish. And then here at 125, so it's like right about here. So you can see it falls a short distance and a bigger distance every time. So now let's take a look at the ball if it's moving sideways. So for this one, we'll use blue. And let's say that it's moving sideways at a velocity of 200 centimeters per second. So in a tenth of a second, it's going to... So the first thing you need to do is take a look at where the ball would be if it didn't accelerate. Remember, this equation tells us what the change is based on the acceleration, but that change is based on where it would be without. So it's changing from its normal path or its non-accelerated path. So as it goes across, if there was no gravity, it would get to the edge of the table and just keep traveling in a straight line at a constant 200 centimeters per second. So in a tenth of a second, it's only going to get 20 centimeters. So in a tenth of a second after leaving the table, it's going to be right here, if there was no gravity. And then a tenth of a second later, it would be here, and then it would be here, and then it would be here, and then here, and on and on. So it's going to travel that 20 centimeters every tenth of a second for a total speed of 200 centimeters per second. Right? Now this tells us, though, wait, If there was acceleration, it would change its height by 5 centimeters in the first tenth of a second. So instead of being here, it's going to be 5 centimeters below that. It's going to be here. And instead of being here, it's going to be 20 centimeters below. It's going to be here. It's going to be below where it was. This is the effect of gravity is having. And then this one would be here. And then this one would be here. So you can see that this blue sphere is actually falling in the exact same way the red one is, staying side by side. The only difference is it's also moving sideways. So you get this curved path through here instead of the straight down path here. Now what if we do one more? What if we say we have a, I don't know, greenish one. And let's let the green one go at a super fast speed. Let's say we're going to let it go at 500 centimeters per second. So every tenth of a second, it's going to go 50 centimeters. So this ball, without gravity, remember, without gravity, it's going to travel 50 centimeters in the first tenth of a second. So it would be here at a tenth of a second. And then it would be at 100 at a tenth of a second. So it would be right here with this one. And then it would be at 150, 200, and 250. So now that's without acceleration. Now we know that with acceleration, it's going to fall 5 centimeters in the first tenth of a second. So instead of really being here, it's going to be here at 5 centimeters. And instead of being here at 2/10 of a second, it's going to have fallen 20 centimeters to here. It's going to have fallen 45 centimeters to here. And that's going to have fallen 80 centimeters to here, and then 125 to here. Now this makes a ton of sense because this force of gravity doesn't know whether or not you're moving fast or slow. It's going to pull the same on you. So as you look here, it's the same fall because of the same force of gravity. So on this one, this 5 centimeters, let me switch over to black actually. This 5 centimeters here is the same 5 centimeters here, is the same 5 centimeters here. And this one that's at 20 centimeters is the same 20 centimeters as here and here. So all three of these balls are falling the exact same way, except they're moving sideways at different speeds, right? And you get those different trajectories from that. So we can look at this problem, we can simplify this complex parabola into a simple straight down falling with some constant sideways motion. Notice for the blue that the amount of sideways motion is constant. It's a constant 20 centimeters every single second, right? It's not getting bigger each time, whereas the height, of course, the height is getting bigger each time. The sideways motion doesn't. And the same thing with the green. The green is bigger, it's 50 centimeters every time. So we can break up this complex parabola into two simpler problems, one that's sideways, one that's vertical. Okay. Now I did want to show you some real video of this. So I have this video of this person doing this exact thing that we're talking about. And what's going to happen here is there's a little spring-loaded arm that'll shoot this way, knocking this ball off while releasing this other ball. And we can look at it frame by frame. We can check this out frame by frame. So here's where the rod's releasing. So it hits that ball off and it releases the other ball. You can see it releases the ball on the left a little bit late, but it's pretty close. Now as they fall, notice they're staying here at the same height as they fall. Same height, same height, same height. Still same height. And they land at exactly the same time. Now the awesome thing about this is you can actually see the bounces. So watch this. As they bounce up, notice same height. As they bounce up, same height, same height, same height. All the way back down, same height the entire time. The the sideways motion of this ball as it shoots this way doesn't affect the vertical motion. It stays the same as one that's just falling. Awesome. Get that out of the way. So our conclusions today, one is that horizontal motion does not affect falling. So things are going to fall at the same rate whether they're moving sideways or not. And the time it takes an object to fall depends on the height it's dropped from and not on its horizontal speed. Right? And remember, our equation for how far something falls is delta H is equal to 1/2 AT squared. And if what we care about is time here, we can easily convert this equation to time, multiply both sides by 2, so we get 2 times the change in height that we're looking for, is equal to acceleration times time squared. We divide both sides by acceleration. We end up with time squared is equal to 2 times the change in height divided by acceleration. If you take the square root of both sides, you get that the time is equal to the square root of 2 times the change in height over the acceleration. So if I want to know if this is a 30-meter cliff, I want to know the time it takes to get to the bottom. I know I'm going to change my height by 30 meters. In fact, it's going to be a negative 30 meters. So I could say here that the time is going to be the square root of 2 times negative 30 meters divided by negative 10 meters per second per second. These two negatives cancel. I get 30 times 2 is 60, divided by 10 is 6, and then I just find the square root of 6 seconds. Okay, and that'll tell me how long it will take for a ball to fall down here if there's no air resistance. Awesome, that's it for now. Have a good day.